Welcome back, everybody. Today in section 7.2, we're going to talk about similar polygons. Okay, we'll explain what that means in a second. It's going to build right off of the work we did in section 7.1 with ratios and proportions. Okay, we'll kind of put those ideas to work with geometric figures today. Now, when we're talking about similarity in geometry, think about a scale map or a scale model or a scale diagram. For example, up above I have a scale diagram of the Golden Gate Bridge. Down below a picture of the actual thing. Okay, and the way these two relate to each other is they're the same shape. The shapes are identical, except for that they're different sizes. Okay, that's the idea of similarity, where we're the same shape but not necessarily the same size. And we'll look at, through this lesson, the implications of that, how that relates to the sides and angles, okay, of these figures. So like we said a second ago, similar figures have the same shape, but not necessarily the same size. Okay, so in terms of polygons, to give two polygons the same shape but not the same size, we'll say they're similar polygons or two polygons with congruent angles and proportional lengths of corresponding sides. Okay, so the angles are congruent, the sides are proportional. Here's what we mean by that. I have two similar polygons. Okay, again, different sizes, same shape. And up above it is a similarity statement. We could say that ABCD, okay, this squiggly line will mean is similar to GHIJ. And what that means is that the angles are congruent. All my corresponding angles will have the same measure. So for example, angles A and G, which correspond, are both 90. They're congruent. Same thing with all the other sets. B will be congruent to H, C is congruent to I, D is congruent to J. So the angles are congruent. And then when we say the sides are proportional, what we mean is that if I look at the ratio of a corresponding set of sides, such as AB over HG, and I make that ratio, that's going to be equal to the ratio of any other set of corresponding sides. So for example, BC over HI will be equal to the same thing, and same thing with all the other sets. Okay, that'll make a little more sense once we give you some actual numbers to work with. But anyways, when polygons are similar, the angles are the same, the sides are proportional. And the last thing we'll talk about quick before we get into problems is the idea of a scale factor. I'm going to say it's the ratio of corresponding linear measurements of two similar figures. So for example, if these are similar, I can get the scale factor by going AB over GH, again, reducing that ratio. And since the sides are proportional, I'd get the same scale factor no matter what set of sides I used. All right, so let's practice using the idea of similarity and similarity statements. So problem 1 says that triangle MNP is similar to triangle SRT. And what does that tell us? Well, first thing, let's figure out what are the pairs of congruent angles. Okay, if we're saying they're similar, that means that all corresponding angles are congruent. So for example, angles N and R correspond. They both look like they're the smaller angle on these two triangles. So I know they'll be congruent to each other. So I could say that angle N is congruent to angle R. Okay, same thing with angle M and S. Okay, it looks like they're both the larger of the three angles on these triangles. So I know they'll be congruent. So by saying this similarity statement here, we're given that also angle M is congruent to angle S. And then a trick we can do, just like we did with congruent statements, I don't even need to use the picture to match things up. Since angles P and T are both the last letters of my similarity statements, I know that they have to be congruent to each other. So just like with congruent statements, we'll match up the congruent corresponding parts in our similarity statement. Okay, so that's the angles. When we say that two shapes are similar, we know that all their corresponding angles are congruent. And we also know that the corresponding side lengths are proportional. Now, what does that mean? Well, part B asks, what are the extended proportions for the ratios of corresponding sides? So for example, what I could do is I could look at the corresponding sides MP over ST. Okay, it's easy to tell they correspond because they're both a shorter side. So I'll make the ratio MP over ST. And when I say the sides are proportional, that means that that's going to be equal to the ratio of any other set of corresponding sides. So if we go with the bigger side next, let's say NP over RT. Okay, those ratios are going to be equal, they'll be proportional. Same thing with the last set of sides. We can look at MN over SR. Okay, all three of those ratios are equal. That's what we mean by proportional. Next thing we're going to do is determine whether or not we're looking at similar figures. So problem 2, part A says, are the polygons similar? We want to know if triangle ABC is similar to triangle FED. Well, to figure that out, what we need to do is check all the angles and see if they're congruent, and then all the sides to see if they're proportional. So let's start with the angles. It looks like both F and A are right angles. So we have angle F is congruent to angle A. Okay, we're also given that angle E and B are congruent. They're both marked congruent with a single arch. So we know that angle E is congruent to angle B. Then as far as the last angles go, D and C, I know they're congruent. And the reason for that is they're the third angles in two triangles with two congruent angles. And our third angle said that the third angles will be congruent as well. If two angles are congruent, the third angles have to be congruent. So we'll just put for a reason here, third angle, as in the third angle theorem. Okay, so the angles work for these two triangles. Okay, all the angles are congruent. What I need to check next is to see if the sides are proportional to each other. So here's how we can do that. We can look at the sets of corresponding sides. It looks like DF will correspond with AC. They're both the shorter sides. So we'll look at DF over AC, which is equal to 16 over 8, which reduces down to 2. Now, if these sides are proportional, all my other ratios will reduce to the same thing. They'll reduce to 2 as well. Okay, so let's see if that's the case. We also have FE over AB, kind of the medium length sides. All right, FB is 30, AB is 15, 30 over 15 is 2 as well. So far so good. And then for the last set of sides, we have DE over CB. So E over CB. That's going to be a 34 over 17, which also reduces the 2. Okay, so that's what we mean when we say the sides are proportional. All their ratios reduce down to the same amount. So for this one, I've got all angles congruent, all sides proportional. So I'm able to say, yes, the polygons are similar. In part B, we're going to take a look at an example of one that doesn't work. So let's take a look at two figures that we will say are not similar. So for the two of these, LMNO and QRST, the angles work. So we'll just say that right off the bat. So I want to check and see if all the sets of corresponding angles are congruent. Now I can see between the two of these, every angle is 90 degrees. So just visually, I can tell they work. But let's see why these two figures aren't similar. Let's look at the two longer sides, LO and RS. Okay, LO over RS is equal to 10 over 16, which we can reduce down to 5/8 if I divide both 10 and the 16 by 2. And the problem I have is when I look at the smaller sides, ON over TS, I end up with a 4 over 6, which reduces down to 2/3. Okay, since my ratio is not the same between the two of these, 5/8 and 2/3, I'd say that their sides are not proportional. Okay, we don't have the same scale factor between the two of them. That's why for this one, I'll say no, I can tell these rectangles aren't similar. All right, so let's start using similarity to do some problem solving. Problem 3 says that ABCD is similar to EFGD, and we want to know what's the value of x. So I have two similar trapezoids, a bigger one and a smaller one. We know some of the side lengths, and it looks like we want to solve for x and y. We'll start off with the x. So here's what I can do for that. I can take x over its corresponding side on the bigger trapezoid, which is 7.5. Okay, so that's a ratio of corresponding sides. And I can set that equal to a ratio where I know both numbers for. Okay, for these two trapezoids, I know what both the left sides are, the 6 and the 9. Okay, I'm going to put the 6 on top because it goes along with the smaller trapezoid, like the x. And the 9 for the larger trapezoid on bottom. And again, since the sides of similar polygons are proportional, I know I have a proportion here I can use to solve for x. All right, so let's go ahead and solve that. We'll cross multiply. X times 9 is 9x is equal to 7.5 times 6, which is 45. All right, cross multiply, then divide. I'm going to divide both sides by 9 here. And we end up with x is equal to just a 5. All right, so x equals 5 would be the length for that missing side there. And again, I can do that because I know the sides are proportional. All right, problem B is the same idea. Why don't you take a minute, pause the video, work through problem B, and then press play to check your answer. So B, same idea. This time we want to solve for the length of y. Now there's some different ways I can set these proportions up. So if you don't set it up the exact same way as me, that's okay. Let's do this. Let's go 9 over 6. So kind of the side lengths we know for the bigger trapezoid over smaller trapezoid. And then I'm going to set that equal to, I'll use the y and the 5 because they're corresponding sides. I'm going to put the 5 on top because that goes along with the trapezoid from the 9 over the y on bottom. Okay, so again, different ways we can set these up. Either way, when we cross multiply and divide, we'll get the same thing. Cross multiply, y times 9 would be a 9y is equal to 6 times 5, which is 30. And then divide, we'll end up with y is equal to a 3.3 repeating. Next, we're going to get into some real-world problems using similarity. Problem 4, part A says, the diagram shows a scale drawing of the Golden Gate Bridge in San Francisco. The distance between the two towers is the main span. What is the actual length of the main span of the bridge? Okay, so we want to figure out the distance between the towers on my bridge, okay, but not in this diagram here, in the real world. Okay, here's how we can do that. First off, let's make a measurement. Now, for the other problems in the note guide, you're not going to have to actually measure, but if you want to use a real scale drawing, this would be how you do it. So I've got my ruler in centimeters, and let's say that that main span we can see here is 6.5 centimeters in the diagram. What I can do is I can set up a proportion using this scale factor here. For my scale, 1 centimeter in the diagram is equal to 200 meters in the real world. So if I want to know how much something on the real world is, how long it is, I'll measure it in the diagram. So here I get that main span is 6.5 centimeters in the diagram, and we'll say that's over x in the real world. Okay, and the way we have that set up is, again, diagram over actual. Okay, a length on the diagram over the length in the actual. And then once again, we can just cross multiply and divide. Now with a proportion, you don't need to worry about converting. That kind of happens automatically for you. So I'll go x times 1, which is just an x, is equal to 200 times 6.5, which is 1,300. And we'll say that's 1,300 meters long. All right, so that's how you use a scale drawing. Why don't you take a minute, pause the video, give part B a shot, the same idea, and then hit play to check your answer. In problem 4, part B, we have a cartographer, or in other words, a map maker, is making a map of Pennsylvania. She uses the scale 1 inch equals 10 miles. The actual distance between Harrisburg and Philadelphia is about 95 miles. We want to know how far apart should she place the cities on the map. Okay, we can take a similar approach to this one as we did with our last problem. Since I know the scale factor of the map, I can set up the fraction 1 inch over 10 miles is equal to, and then this time I'm given that it's 95 miles from Harrisburg to Pennsylvania in the real world. Okay, so I'm going to put my 95 miles on the bottom, okay, with the 10 miles, okay, corresponding with the real world. And then this time my x is going to be on top. I'm looking for how many inches we have on the map. Okay, so that x will be different depending on whether we want to find the value in the model or in the real world. Once we have that set up then, cross multiply. 10 times x is just 10x is equal to 95 times 1, which is 95. And divide, we can divide both sides by 10. That's going to give me that x is equal to 9.5 inches for the distance on the map. All right, we've got one more real world type problem for you. And this is going to be something that happens anytime you take a picture on your phone and try to either print it off or display it on a different screen size. We'll show you what the issue with that is. Let's say Mr. Bailey wants to take a 7-inch high by 5-inch wide picture and blow it up with his projector. The space his projector covers is 42 inches high by 56 inches wide. We want to know what's the largest picture Mr. Bailey can display on his projector. Okay, so I don't have my projector out here, but my screen does the same thing. So let's say I want to take this picture, this 7 by 5, and blow it up to fit the screen. Now you'd think the biggest I can make it would be the 42 inches high by 56 inches wide. But here's the issue when I do that. Notice what's going to happen to Pluto here is he's going to get stretched out more wide than tall. Okay, so I can stretch him to fit the whole thing, but my picture gets distorted. I'd say I don't have two similar pictures. Okay, notice this nice skinny dog here. And again, he gets wider as we stretch him out. So what I need to do is I need to, well, fix my aspect ratio and figure out how much I can stretch him out where I fit the height of the screen perfectly, but make my width so that it's still a similar picture. Okay, the way I'll do that is the same way that we did the last question. We'll set up a proportion and make this smaller so I've got some room to work. Okay, I can use the original picture, the 7 inches high by 5 inches wide, and go 7 over 5. And then we fit the height perfectly. So I'm going to say the height of my new picture is going to be 42. I don't know what the width is going to be. Again, my height fits as 42. My width is, I'm not sure. We'll call that x. And then once again, I can just cross multiply and divide to figure out what the kind of fitting width is going to be. 7 times x will give me a 7x is equal to 5 times 42, which is 210. Divide both sides by 7, and we'll end up with x is equal to 30. Okay, so my biggest
picture I can have then, it would be 42 inches high by 30 inches wide. All right, that's it for lesson 7.2. Okay, geometric similarity with some real-world applications to it. Start going to town on the homework, start getting your practice in. Let us know if you need help, and we'll see you folks at the next lesson.